Now we'll talk about a much more efficient approach called the simplex algorithm. This actually will not be polynomial time in the worst case, but as a practical matter, this algorithm is efficient enough to be widely used. The simplex algorithm allows us to move from one basic feasible solution to a better one, and by moving to better and better basic feasible solutions, we eventually reach the optimum.
For convenience, let's suppose that our current basis consists of the first m columns of A. We'll call this submatrix B, and the remaining submatrix D. It will also be convenient to partition X and C in an analogous fashion. Overall then, we can write our standard form linear program like so. CB transpose times XB plus CD transpose times XD, subject to the constraints that B times XB plus D times XD must be equal to B. And of course, both XB and XD must be non-negative. For the simplex algorithm, we want to consider the effects of swapping out one of the current basis columns for another one. To do this, we first want to identify a good candidate for moving into the basis, one that will improve the objective function. As the program stands, however, it's not immediately clear which, if any, are good candidates. Sure, for some xi in xd here, the corresponding coefficient might be positive, but raising the value of that variable might force others to change because of the constraints, making the whole picture rather opaque. Therefore, it will be convenient to parameterize our ability to move around in the flat defined by these constraints solely in terms of the variables in xd, the variables that we're thinking about moving into the basis. By the way, I'll use the idea of moving variables and moving columns into the basis interchangeably throughout. To this end, we solve the equality constraint for xb so that we can substitute for it where desired. First, we substitute it into the objective function, and through a little manipulation, we get this expression. This constant term here doesn't matter, since we're only considering the effects of changing xd. This quantity that gets multiplied with xd, however, is important enough that it deserves its own name. We'll call it rd. In our reframing of the problem, therefore, we want to maximize rd transpose times xd. How about the other constraints? Well, the first one goes away with the substitution. This requirement, however, that xb be non-negative remains. Substituting our equation for xb, we get the constraint shown here. Of course, xd must remain non-negative as well. Note that xd equals 0, the current situation for the algorithm, is feasible, and it's easy to see a way to improve the objective value just by looking at the vector rd. Our real goal, however, is not just to climb uphill, but to figure out which column should enter the basis.